Welcome to chapter 10. This is the rotation of a rigid object about a fixed axis. I'm Sorasak Phanphak. So this is the part of the course of 0142 to 0111, the general physics ones from Kasetsart universities. The rotation of the rigid object is the things that you maybe mostly get used to, but to simplify, we would like to identify the object of interest as a rigid object first. So what is the rigid object? This object cannot be deformed. So it's a kind of undeformable object. So it still stays still like that. Even you have a force exert on it, it's still in its shapes. So for example, this is the T pot. This is not any deformation. When you do any rotation, they have some kind like quantities that state about the way to resist a thing of the making it rotate. In this case, this I call the moment of inertia. You will learn that different objects rotate in different axes, have different moment of inertia. So this is not only the teapot, also any others geometrical shape, for example, like a dish or a ring, or maybe a solid sphere, or maybe the cavity sphere like this one, or even a rod. So if you try to rolling these objects down the slope, the influence of the moments of inertia or the thing that resists object to rotate influence to the terminal velocities of these objects. So that means the higher moment of inertia may resist the object for a rotation, so it may go to the you can see the final line at different times. So that means the rotation is rotate at different rate due to the moment of inertia. And this all thing is all about thing that now not going through the central mass or the central of the objects. So we have some torque involved into these type of phenomenons. And the torque is the cause that make these objects rotate. So you will learn about the angle rotation and also about the torque, which is the influence to make this object rotate. And the moment of inertia, you will know how to find it. As I already said, the rigid object is non-deformable objects. Whether you have force exert on it or the torque exert on it, they're still in its own shapes and remain constant, but I varies depend on the axis of rotation. We will emphasize on this part later. So what is the angular position, angular velocity, and also the angular acceleration? You may get used to the linear position already, right? Which is maybe you are any position. You can write it as positional vector or just r as a position. The linear velocity is the vectors of the speed that you did learn about it, and acceleration in linear we write down things like this. But for angular position, we rather not using r, we interest in how this particle, especially particle p, changing in terms of angle or this arc happen. So angular position we define as a theta. That means the angle or the arcs or the angular position that this particle specifically p moving along. Maybe this is a CD this, and we define theta as an angular position. For how about the angular velocity? Rather than you have v, we define omega as an angular velocity. And with the acceleration, we define alpha as its angular acceleration. since you already know, if you have the position and you have the change of position with the times, so you have the velocity. So this is also, if you have the change of the angular position with the time, you have the magnitude of the angular velocities. Thing is like you finding the speed if you don't care about the vector, but you can put the vector indicator later. So I will teach you how to identify the direction of the angular velocity later. So for an acceleration, if you dip v by dt, you will have then a. In this case, if you dip omega by dt, you will have the angular acceleration. We will know about this relation in more detail for the later session. For start with, if we would like to determine about the angular position, we should have some reference as the initial state. And in this case, we use polar coordinate to represent the motion or the position or the change of the particle p. So with the polar coordinate, you have r to represent the distance from the axis to the position of your interest, that is r. And the theta is angle the sweep from the reference line. With this relation, you can see if this theta is quite small here, and this is your r and this is your s, you will find out like the theta is about tan theta, it's also s over r. So if you would like to determine the displacement along the tangential part, which is this s, you can redefine it from the angle or the angular position that is sweep from the reference line multiply with the radius or the position in the radial directions. So this is the definition of what you can convert the arc length, which is the S1 is the arc length, to the angle. So this is the relation. So you can see it as a linear relation to the angular relation. This is angular. So not only the arc length or the displacement or distance over here, then you can convert the tangential velocity or also the tangential acceleration. You can convert back compared to the angular velocities and the angular acceleration as well. You will learn about this soon. So from what I did state before, if you would like to convert between the angular and the linear, which is this is the arc length, you can use this kind of relation to convert, and unit of the theta is in radians. And if you determine it carefully, so you can have theta as a radians in unit or degrees, for example. But if you look after this type of relations, so you put the dimension into it, like this, you can see the arc length and r is in the same unit. They are in the same unit, meter. So that, but alternatively, you can see this is a kind of dimensionless as well. We will know about this later when we would like to claim about the unit of the angular velocities and also the angular accelerations. However, if you would like to convert between a unit of radians to the degrees, as you know, 1 radians, you can redetermine, for example, a whole circle is 2 pi radians, which is a whole like a round of the rotation is cost like 360 degrees. So that means you have 2 pi radians at 360. So if you would like to find 1 radians, it's 360 over 2 pi, which is 1 radians equal to 57.3 degrees. And you can do this kind of conversion, change it from radians, change it from degrees to radians, if you want to do any conversion between these two units of the angular position. Next, if we would like to determine the displacement, since before we determine the angular position when we compare with the reference, so this is the angular position that you compared it. However, the initial angular position can be any due to the motion of the rigid object that you're looking after, or the particle in this case. If this particle moving from point A to point B with the time difference as Tf minus Ti, as you can see, initially at point A, they have the angular position as theta I. And when the time change at the position B, they have the angular position as the theta F. So you have the displacement. Displacement is like you have in the linear displacement, right? Is the final position compared to the initial position. So this is your Rf minus Ri, or your delta R. This is the linear displacement. However, in the angular displacement, you also have some difference of the angular position as well. So by this, you can see that, for example, you can determine the displacement here. This is the delta theta from the position A to position B. Using this relation is similar to the linear displacement, but now you determine the angular displacement instead. So when you have the change of the displacement in your linear information, like in linear, the change of displacement in terms of vector, or maybe we only care about the magnitude first, and then we can put vector in later. The change of displacement, the displacement with the time is the velocities. In this case, if you try to determine it, you have the average of the velocity. If you find the change of the position in the infinitesimal of the time, so you will have instantaneous velocity. These are in the linear that we did learn, and we're quite clear about this point. However, if you look after the case of the angular speed or angular velocity, if we would like to care about magnitude only first, and I will show you how to convert this information to your vectors. You can also find the average and the instantaneous of the angular speed as well. For find the averaging, you just determine the delta theta over delta t. For identify the instantaneous, just use the differentiations of this theta over dt. And by this, you will have the average omega, which is the average angular speed in this case. Because you don't put any vector sign, it is still not yet a vector, it's still a scalar. But to let you know, all these quantities are vectors. We can have the vector size afterward if you want. So this is the average of the angular speed, and this is also the scalar, which is the speed that we look after here. But when you dip it, you got the instantaneous angular speed. This is also the scalar. How about the unit of the omega? It can be radian per second. Write out like this, radian. my pen is quite messy now, sorry. Radian per second. Or if you consider about the theta that equal to S over R, this is the dimensionless. So you can ignore the dimension of the radians. So you can have another unit of the omega s per second. So this can be radian per sec or per second. These are for the unit of the angular speed. You already know about the angular speed or angular velocity if we put the vector in later. Now, the angular acceleration also derived similar to what you learned from the linear accelerations. Since the linear acceleration, if you would like to consider only the magnitude of it, it equal to delta v by delta t. This is the way that you try to average from the initial point to the final. So this is your A average. However, if you like to determine any instantaneous accelerations, I mean in different positions, so you just using the differentiation on dv by dt. So this is for linear acceleration. So if you like to determine the angular acceleration in average or in instantaneous, you also can use the same idea. So you just have delta over delta t. So in this case, supposed to be delta omega over delta t. And in instantaneous, you can have the dip by dt of the omega. So this is how you find the average angular acceleration for this case. And you can also find the instantaneous angular acceleration as well. For the unit, it can be radian per second square, or if you ignore or think the radians as a dimensionless, which is from the theta itself, you can have another unit as the second per second square as well. So you can write like this: second minus 2. Whether you have radian per second square or per second square as a unit, it's really okay for the angular acceleration, whether it's average angular acceleration or instantaneous acceleration. Now, as I already said, all these quantities, as you know, the displacement, the velocity, the acceleration, they are vectors, right? How about the theta, omega, and alpha? They are also vectors as well. But the way to determine the theta, the angular displacement, is slightly different compared to omega and alpha. If you like to determine the direction of the omega and alpha, you have to use the right hand rules. And the way you use your palm and wrap up, the way that you wrap up is supposed to be in the direction exactly the same of the direction of the tangential velocities. For example, if this case is have the tangential velocity over this part, as you know, the relations, which is from the definition of S equal to theta r. If you would like to find the V, which is S is the arc distance here. So V is the way you dip S by dt so that you have V tangential here. And you also dip theta here, you have omega r. So that means you have the relation of omega r and then have the V. So if you wrap up in the way of V moving around like this plane, so the thumb that you're pushing upward is the direction of omega. However, if the tangential velocity of the way that this object rotating around the axis, moving in different directions. So if moving counterclockwise direction, you have the omega in this direction. If it's in the clockwise, which is this direction, you have omega pointing in another direction. So by this type of relation, now we can put our omega into a vector. Since if you know the direction, for example, in this case, you know the axis, like this is x-axis, this is y-axis, and we moving like this part, so you have omega pointing upward. So in this case, is you wrap up your palms and you have your thumbs pointing upward. This is the direction of omega for this motion. So you can write omega as the omega in z direction in this case. Or you know that omega is v over r, that in z direction. Since you know the tangential velocity and you know the radius of this object and moving as a circular motions, and this is also involved with the angular motion of the object. If we would like to determine rather than the SVA, now we move it to theta, omega, and alpha. Since we would like to determine or define the quantities in terms of angular representation, so you rather use the polar coordinate rather than the Cartesian coordinate.